Yesterday we left off talking about areas, polar coordinates. We started talking about polar coordinates, and then we started talking about areas, and then we had to leave for some stuff. And so today we're going to pick up with areas, and then we're also going to start talking about arc lengths. And if we have time, we'll get started with conic sections. So last thing we talked about was for you to try to figure out, tell me the area of a circular sector, if this is coming from a perfect circle. What is the area here given that this is R and this is theta? Anybody figure that out? Theta over 2r squared. Okay? So whether you dug that up from somewhere, you derived it from somewhere, then that's what it is. So it's based on, or one can think about this as being based on the ratio of this area versus the area of the whole circle of radius r. So in any case, this is what we have. We have a formula for this thing. Now the idea coming from this formula is to try to find, we have polar functions, r is function of theta, being drawn out for some value of theta. Now this could be whatever it's going to look like. An example that we had was a cardioid, or it could be a spiral or whatever. So it's whatever it's going to look like going around at some value of theta. And so we might be interested in finding the area that's, we wouldn't say it's below the x-axis. That doesn't make sense here. We're looking at the area from the origin to the graph, and that area being spread out over some values of theta. So we have, we could take a look at a couple of angles, theta 1 and theta 2. And then we want to find this area over here. Maybe I should do that in a different color. And when we're finding areas, just like we did with the first semester or second semester calculus, is to break it up into smaller pieces. So the smaller pieces that we're going to consider will be, instead of a vertical slice, because a vertical slice doesn't make sense here, what we're going to do is we're going to take a look at a slice of a pie, so to speak. Let's see if we can blow this up a little bit. So we're going to break this up into slices of pies. The only disadvantage we have is that we have this formula for a nice circular sector. And this is not necessarily a part of a circle. Right? You see where that issue happens? Well, what we did in calculus, if you remember back, is that we didn't look at rectangles with a smooth curve on top, right? We look at rectangles with a flat top, and then we just called it an approximation. So we can kind of like do the same thing and call this a little approximation, pretend that this is actually a circular piece, a piece of a circle, and just approximate it. And then what's going to happen is that you're going to break up your pieces into smaller and smaller pieces, and then your approximation gets finer and finer. Okay? So let's say between theta 1 and theta 2, you're going to break this up into smaller pieces. The angles that we're going to have are going to be broken down. Let's say it's going to be broken down into equal angles. And the angle that we're looking at here would be your change in theta, delta theta, just like the change in the base, delta x. And then for some value of theta, it could be the right endpoint or the left endpoint or the midpoint or any value in between. We'll just say that that's theta star. And to get the radius, you just put theta star into the function, and then that's going to give you your approximation for that one little sector. So for this one little sector, the area, and I'll put sub I here because let's just say this is the ith area, is going to be, according to the formula, 1/2 theta r squared. R is f of theta, and we're putting one particular value of theta. And then the angle that this has is delta theta. Okay, so this comes directly from the formula where we have r and theta and the 1/2. Oh, yeah, that has to be squared. Let's square that. And now, this is one little small slice, and we're going to add up a whole bunch of them. So when we add up a whole bunch of them, this right-hand side is going to become a Riemann sum, which is then going to become an integral if we take it to the limit. Okay, so this is the magic of calculus, exact area will then become, let's call it A is equal to, and then this Riemann sum becomes an integral of 1/2 f of theta. The delta theta becomes a d theta operator, and then here we have limits from theta 1 to theta 2. Yes. I keep not wanting to square it for some reason. Yes, so f of theta squared. So now it becomes a formula for us, but going through the derivation takes us back to calculus, right? Takes us back to Riemann sum. Calculus 2, you did all kinds of different applications of the Riemann sum. And so we'll continue to do some of those applications, but this is just a little refresher to try to get you to think back of Riemann sums again. So the Riemann sum becomes an integral. Now we have a formula for finding the area that's going to be bounded by a polar coordinate graph. Okay? So we had a problem, a cardioid problem the other day. Where we might be interested in finding the area in the first quadrant. So remember that formula, R is equal to, was it 1 or 2? 2? 2 minus 2 sine theta. So we're basically done here. We just plug in the formula, and that really doesn't take much work. So all we need to do is treat this as your f of theta, and so this and then the other difficult part probably will be trying to figure out your angles. So theta 1 is going to be equal to 0. That's your starting point, and theta 2 is going to be pi over 2. So those will end up being your limits of integration. You have your f of theta here. You're going to want to square that, and then that's it. So your area is going to be the integral from 0 to pi over 2 of 1/2. I guess you could take the 1/2 outside. And then you have 2 minus 2 sine theta squared d theta. So these types of integrals, to me, are not very important. This is not what the class is about. I'm assuming that if you had to struggle through this, you should be able to compute this by hand. But in most cases, I'm not going to care about how to compute integrals. There might be some times where if the integral is simple enough, then that's not a big deal. I think this integral is simple enough. You FOIL it out, and then there's going to be a sine squared, which is going to be the toughest integral, but everything else shouldn't be too bad. But in most cases, I'm just going to, especially in test or quiz situations, I might just ask you to set it up, and then that's all I would want. Or I might have you carry out the calculations in your calculators, and I hope that you know how to find the integral in your calculator where you would get a numerical value. Okay, so those would be the things to look out for. At this point, I would consider as done, and then you just take it a step further if you're going to need to find that numerical value. And for those cases, might I suggest Wolfram alpha, where you just integrate 1/2 times 2 minus 2 sine theta or t squared. Take that integral with respect to t from 0 to pi over 2. So usually these, you can get away with a lot of just typing in like common keywords as a math person. You say integrate, and then you put the function down, you put some limits down, like whatever your limits are, like I did over here, and then Mathematica or Wolfram thinks about it and then tries to read your mind as to what it is you're trying to say without having to learn the actual computer language. So if we were to find the actual value for this, we have 3 pi over 2 minus 4, or 0.7. Okay, any questions? What's the area of the whole thing, the whole heart? Remember, you're only giving a quarter to your Valentine's? So what proportion of your total heart did you just give away? Well, it's not going to be 1/4 because this area looks a lot smaller than the rest of them. You only gave them the right atrium. So it's the same thing, except you're going to take the integral from 0 to 2 pi. So let's figure that out. So area of the whole thing is going to be the integral from 0 to 2 pi of that very same function that we just integrated. So let's go back to Wolfram, and all I have to do is change the limits because I still have this information here. I'm just going to go from 0 to 2 pi. And then it's 18. It's 6 pi. Whoa. So what percentage did you give your Valentines? Pretty small percentage, huh? 0.7 divided by 18. What's 0.7 divided by 18? I think it's 0.7, because this is the proportion, this is the portion that you're giving, and this is the rest of it that you're keeping. Well, not that you're keeping, but. So, no, I'm not going to write that. So you only gave about 4% of your heart to your Valentine's. That's messed up. Okay, any questions? All right, some of the other things that you'll tackle would be like finding the area between two graphs. And for that, that gets a little trickier. And I don't think I have any problems set up for that. So maybe you'll take a peek at your homework and maybe try to do one of the homework problems. This is 10.4, I think, yeah? Oh, you have some labs due on Monday, Tuesday. Make sure you do them. Find the area of one loop. Now here's an interesting one. Find the area of the region that lies between the first curve and outside the second curve. Let's give that a try. And I hope that you've been messing around with your graphing calculator or with some other program that allows you to graph polar coordinates so that you can get a feel for what these things might look like. Like, what do you think the first one's going to look like? Is it going to be a circle, a cardioid, a limaçon, leaf, rose, donut, infinity sign? What is it? It's a circle. It's just a circle. And what's the second one look like? That's just a circle too. All right. So it would be ideal if you can actually view this using your graphing calculator. Because plotting points, when it comes to graphing these things, plotting points would just take a really long time. And if you don't get enough fine points, then you're not going to get anything that's meaningful. So I think this starts off with 14, and then it does a couple of circles like this. If you go from 0 to 2 pi, if you go from 0 to pi, you'll just be able to draw that one circle. And this has radius 7, and so I think that's this over here. So if you don't see that right away, or if that doesn't come to you right away, then make sure you graph it just to get an idea of what this thing might look like. And here is your r is equal to 14 cosine theta, and here is your r is equal to 7. Now let's read this again. Find the area of the region that lies inside of the first curve. So this is the first curve right here. Let's draw this in orange maybe. Inside of this first curve and outside of the second curve. And so this is the second curve, and outside of that would be over here. So where is the intersection of those two things? Is it this one? Is it this one? Yeah, it's that one, right? And it's not anything else outside. So this is the area that we want. So out of this, what we need are a couple of angles. We need to figure out where they intersect so that we know when to start and stop our integral. Oh, by the way, since you are looking for areas between curves, just the same kind of logic that you found in Calc 2 where you found areas between curves, it's just the top minus the bottom. Oh, the top minus the bottom. Which one would be the top curve? The one with the cosine? So this is the top curve. And this is the bottom curve. So now we just have to figure out where they intersect. Where do they intersect? How do you suppose we're going to find the intersection? Set them equally. That's like the rule that we've had since algebra, right? If we want to find where two things intersect, we set them equal to each other. So we'll set them equal to each other, and they look like they're both equal to r, so it kind of makes sense to set them equal to each other. 7 is equal to 14 cosine theta. Well, this will turn out to be nice, I think. Maybe not. 1/2 cosine theta. So is cosine, maybe it's not so nice. I was going to say root 2 over 2, but cosine of root 2 over 2 is cosine of, what? Cosine of pi over 4 is root 2 over 2, but this isn't root 2 over 2. So I think we might just have to say theta. Is it pi over 3? Yeah. Oh, okay. So it does turn out to be a nice angle. So theta is equal to pi over 3. Remember your trig? A little bit of trig, a little bit of algebra, a little bit of calculus. All right, so there's two of them. Probably positive and negative pi over 3 would be good candidates for this. But one of the things, since we are going around in circles, it'd be good to remember to take advantage of symmetry if there's any symmetry going on. So instead of going from minus pi over 3 to positive pi over 3, maybe we can just integrate from 0 to pi over 3. Okay? And then double it. So let's just say our theta goes from 0 to pi over 3, and then we'll double that, and then we'll get things set up. So I think we're good. So let me just rephrase the function, or the formula for the integral between two curves, and I'll just write f1 and f2. So your area between two curves is an angle integral from theta 1 to theta 2. Now you have two functions that you're going to take the difference from. There's a 1/2 in there, so let me throw the 1/2 out. And then the other thing that happens is that there's that delta x that becomes a dx. So in between here is going to be the difference between the two functions. And you have to square them first and then take the difference. So this would be f2, the bigger function of theta, squared minus f1 of theta squared. So you need to square each one separately and then do the subtraction. All right, so now that we know all that information, we can just find the area here. A is equal to integral. Let's say 2 times the integral from 0 to pi over 3 of the 1/2 that you can take outside and cancel with a 2. The outer function is 14 cosine theta, so let's square that. And then the inner function is 7. Let's square that. And then we have d theta. And then we can just punch it in the calculator and get our answer. Now, depending on your homework problem, they may want an actual value, an exact value, or they want an approximation with your find the area region. It doesn't say what they want. So usually if it doesn't say what they want the actual value, the exact value. Let's try putting in both numbers and see what we get. First, I'm going to ask Mathematica to figure it out for me. So it'll be 2 times the integral of 1/2, and then my first function was 14 cosine theta, and I want to square that, minus 7 squared, let's just say 49, and we want our t to go from 0 to pi over 3, right? Yes. That would be useful. Thanks. Yeah, and say this is what you had put. So 14 squared is 196, and here we go. We have 2 types of answers. Let's try the numerical value and see what they say. And if you get it wrong, you can put in the other value. 93.75, let's say. 93.75. And if they don't like that, then try putting in the exact value, which was 49 root 3 over 2 plus 49 pi over 3. Yay. So, here you go. That is, thank you for coming up with all that stuff. So, we have formulas that we can use. We have Wolfram Alpha to help us compute integrals to punch into your homework assignment programs and get some approximations, get some values. Okay, any questions? All right. So the next thing is to look at arc lengths. Yeah, so by the way, you know, the stuff that I'm going over in lecture are things that might be related to your homework and that could be related to your exams and quizzes and stuff like that. But I'm not necessarily going to cover every little aspect of finding things out. So like you might be struggling and trying to find when 2 graphs intersect, and if you can't find it using, you know, what we just did by setting them equal to each other, you might have to actually graph it and take a look at where those limits, you know, if you change the limits in your window so that you can see where it goes, and that will allow you to see what the actual limits are for your integration. I think that's going to be the most difficult part in these types of problems, is finding the limits of integration. Okay, finding when 2 things intersect, or finding when you're able to draw a piece of the graph that you're trying to draw. Like the limaçon with the little hole in the heart. Ooh, hole in the heart. That, you know, trying to find out where what the limits of integration are for that could be tricky. Also, when your R gets negative, it gets kind of tricky too. So those are a lot of things to think about, and you're not going to be able to think about them until you actually start doing these homework problems. So do the homework problems, struggle a little bit, look up stuff, and then ask questions, and then hopefully you'll pick it up. Okay? All right, let's move to arc length. Here's a formula for arc length. We can derive it. If we go back and take a look, change it back into parametric equations, and once we do that, we'll use, because we have a formula for the arc length if we have parametric equations, right? So if we use that information after we change it to parametric equations, we should be able to get this formula. So let's just do that kind of quickly. If you remember, your polar coordinate r is equal to f of theta can be translated into parametric equations with x is equal to r cosine theta, y is equal to r sine theta, and r is equal to f of x, so, or f of theta. So your parametric equation will look like this. And if you remember the formula for finding the arc length, if you have parametric equations, it's the arc length is equal to, let's call it length, is equal to some integral from alpha to beta of the square root of x prime. You say dx dt, I'm just going to say x prime of t squared plus y prime of t squared dt. So if you just take this x and you take the derivative of that and square it, and you take the y, take the derivative of that and square it, and then there's going to be a bunch of sine squared plus cosine squared business, which will end up being equal to 1. And then that'll bring you to this formula after you do all the simplification that you need to. So we can find arc lengths of things, of polar coordinates now. We can find the arc length of the cardioid that we were working on. Arc length of the cardioid from 0 to pi over 2. All right. So again, since we have the formula already set up here, there's really nothing much to do aside from plugging it in. You have your r, that's f of theta, and then you need the derivative, and then you just plug it into the formula. So let's do that. We need r prime. That's going to give us your f prime of theta is equal to constant, and then the derivative of sine is cosine. That remains positive, so the negative outside of that will stay. So then the length here, they call it s, we'll call it s, is equal to the integral from 0 to pi over 2. Those are the limits that we were asking for. And then the square root of, the first one is the derivative. They're adding, so it doesn't really matter which one goes first. And the negative doesn't matter either because it's going to be squared. And then the original function, theta. Okay, so in the old days you'd do this by hand, calculate, but now we're just going to plug it into our Wolfram alpha and see what we get. So we're going to integrate the square root. So SQRT, I think it's the abbreviation for square root. I know that's what it is in Mathematica, but if you don't remember the square root in this, you can just raise it to the 1/2 power or 0.5 power. Just make sure it's in parentheses. So the square root of what? So we have 2 cosine theta squared plus, in parentheses, 2 minus 2 sine theta squared. And then close the square root. We're going to integrate this from 0 to pi over 2. Oh, there's a 2 in here that we don't need. Didn't use my parentheses wisely. All right, what am I missing? Another parentheses? And then am I good? Maybe one more? Yeah, so I close that parentheses. Let's see. Does that look okay? Yeah? Looks good. So remember, the challenge in this class isn't computing the integrals, because the machine can do that for us. The challenge is looking at a problem and seeing how to set up the integral that you need to set up. Okay, to me, that's a bigger deal in this class. If we were doing Calc 2, then we would be computing these things by hand, and that's important. But assuming you passed Calc 2, that's why you're here. So we're done with that. Okay. So they can ask for one loop of a rows, a 3-leaf rows, or some other function like that. So again, the most difficult part is trying to figure out what your limits of integration are. Trying to see, and then using, if there's symmetry to be used, take advantage of that. So instead of going from negative angle to some positive angle, you can just go from 0 to angle and multiply by 2. So that would simplify your work a little bit, and that will get rid of any possibilities of overlaps, because the sine and cosine, these trig functions are periodic functions, so weird things happen sometimes when you go to the negative parts of things. So be careful with that. We want to take advantage of symmetry as much as we can. Okay, any questions? Yes? Uh-oh. Oh, yeah, because it's squared, it becomes positive anyway, so. Okay. Anything else? All right. Just one more peek at these problems that you have for this section. Pole? What's a pole? All right, you guys have to figure that out. Arc length. Use a calculator. One loop. Find the area and then sketch it. I think you guys are good after you figure out what a pole is. All right, we're going to move on to the next section. What is the next section? Do I have the next section? Conic sections. So this section talks about conic sections, and unfortunately, it's a lot of looking at formulas and I don't want to say memorize, but kind of identifying yourselves with the form of the equation so that you can graph or at least be able to identify what kind of graph you're looking at. Okay. So for these things, we're looking at different types of functions, or not functions. I wouldn't call them functions. I'd just call them graphs. So the conic section creates graphs based on relationships between x and y. So graphs based on relationships between x and y. And I don't want to say function because a lot of these things may not look like our traditional function that we know of, where we can say y is a function of x, or even x is a function of y. If you take a look at pieces of these things, they might happen that way, but it may also not happen that way. So we have a handful of types of graphs that we're going to consider. Parabola, circles, ellipsis, and hyperbolas. And a couple of other types here that I'm not going to write down is a point and a line. Technically, that falls under the category of conic sections as well, but we know how to deal with points and lines already. And if you've seen something like this in your textbook or in a pre-calculus textbook, you see they call it a conic section because these things come from a cone. From a cone, then you're able to make slices with a plane, and you come up with these types of figures. The way they're defined is a little bit different from the way we know of a parabola or even a circle and an ellipse. And they define it using measures of distances. They say these are all points on the xy plane such that the distance between this point and this point is the same, or something like that. So that's how we're going to try to approach it, and then we're going to see if we can come up with these equations that we'll use. Parabola. For a parabola, you need what's called a directrix and a focus. Again, the definition is strange, but this is how they define things in math sometimes. A parabola, a set of all points that are equidistant from a fixed point, called the focus, and a line, a fixed line, called the directrix. And there's a special shortest distance between the point and the directrix that's going to be called the vertex. So without any axes and just looking at a point and a line, what we want to do is we want to find all the possible points that are equidistant, the same distance from your xy point somewhere in space, as long as it's going to be the same distance from the point, the focus, to the directrix. So if I randomly pick a point somewhere over here, the distance from that point that I randomly selected to directrix is going to be this length, whatever that is. And then the point to the focus is going to be that. Now, is that equidistant? That's not equidistant, right? If we pick a point right in between the focus and the directrix, is the distance from the focus to that point and that point to the directrix the same distance? Yeah, in fact, this is the midpoint between the focus and the directrix. So yes, this is a good point, and this is in fact called the vertex. So if I pick another point over here randomly, I see that that distance over here between the point and the directrix doesn't look like it's the same as the point to the point. So that's not part of my list. But if I move it down a little bit, so that they have the same distance, now that could be another point on my parabola. Right? So if you could imagine picking another, even this far over here, if I pick a random point over here, as long as the distance from that point to the directrix and the distance from that point to the focus is the same, that will be part of my parabola. And if I find every single such point, you'll see that it'll be in the shape of a parabola. The parabola that we all know of as a parabola. Okay? Yes? The vertex is the lowest point of the parabola. Well, it depends. If the parabola is turned the other way, if your focus, yeah, but it's going to be a special point in the parabola for sure. So if your parabola goes down, then it's going to be the highest point. And we also will allow for parabolas to go sideways, because we're really just looking at a relationship between a line and a focus point. It creates that shortest distance, yeah. It's the shortest distance between the focus point and the directrix. And this is your vertex. So you can think about it as the lowest point if you tilt your head the appropriate direction. Even upside down. Turn your head upside down. Okay? But it is a special point. So the next thing to do is to try to figure out how to write this as an equation in terms of x and y, because it is, in fact, the relationship between x and y. So we should be able to write an x and y equation with this thing. For that, we just look at the formula here. A parabola with vertex point and a focus point and a blah, 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 blah. Looks like that. All right, there you go. So we define vertex. The vertex is going to be that special point. Parabola with a vertex at the point B comma C with a focus point B comma, they make this kind of weird because they want to make it fit nicely into a familiar formula that we know of or that we want to continue to use. So your equation of that parabola is y is equal to a parentheses x minus b close parentheses squared and then a plus c. And that gives you your standard equation of a parabola. So this would be a parabola that's pointing up or down. Your line, your directrix kind of tells you the orientation of the parabola. Your directrix is a y is equal to a constant, so you know that's a horizontal line. And if you have a horizontal line, your parabola is either going to go up or down. If your directrix is x is equal to something, then that's a vertical line, then of course your parabola is going to go sideways. So these 4 pieces of information, your vertex, your focus point, your directrix, and your equation, kind of give the whole picture for that parabola, for that graph. And some of the tasks that you might be asked to do is that if you have the equation, can you find all the rest of the information? Or if you have 2 pieces of information, can you find the equation? And it's just being able to relate your parameters A, B, and C in terms of this function. And its components, your directrix, your focus, and your vertex. Okay, so let's do a problem related to this. Let's, I think I might want to copy this. So let's say we had an equation of a parabola. We know that this is a parabola because it's a second order polynomial, right? Let's identify, all the different things that we need to identify. Let's find the vertex, the focus, and the directrix for this. Well, I'd like to just be able to pull out the A, the B, and the C, but I can't seem to do that because it's not written in this form. Guess what you need to do? What? Complete the square. Remember how to do that? When you tutor your students in Algebra 2, when they have to complete the square? You're not tutors? You should go be a tutor. You guys are in Calc 3. You guys are going to be using algebra all the time. If you're not an algebra tutor or a calculus tutor, you should sign up to be a tutor. What? 7 outside. You can put it on the other side, but I'm going to keep it on this side just because the equation has it kept on that side. So let's do that. So take the 7, just write it a little bit further out. And then what we're going to do is we're going to write the x squared minus 3x here, and then we're going to figure out something to add and subtract so that it doesn't change the actual equation. And do you remember what you add in here? Half of 3, so negative 3 squared. You're going to square it anyways, right? So that goes in there. That's going to be, you take half of that and then you square it. So half of that is 3/2, and you square it 9/4. Or what is it? 2.25. And then you added it inside, so you need to subtract it outside. And so what do we have left? We have, let's complete the square. And this is going to be a perfect square now because you added the right number. So it's going to be the square root of 9/4, which is 3/2. And just for the sake of keeping all the fractions, let's make this into 28 minus 9, 19, 19/4. Okay, 37/4. Oh, it was a minus, yeah?
Oh, minus.
Yeah. All right, so now we can figure out what A, B, and C are. A is equal to 1. That's nice. B is equal to 3/2. That's nice. C is equal to 19/4. So it's your vertex. Three halves, comma, 19/4. And your focus, 3/2, comma, oh, this stuff. Yeah, it's 19/4 plus 1/4, right? Or is it A is equal to 1? Yeah, 1/4. 20/4? 5? Is it 5?
Yeah.
5. And then your directrix. So remember, the directrix is actually a line, so it's an equation of a line. We want to write it as an equation, so I write y is equal to. So instead of adding 1/4, you subtract 1/4. What do you end up getting? 18. Let's do 18/4. Oh, let's 18. That's 9/2, yeah? 4.5. Okay. Let's see this in the graph. Oh, I was going to show you guys a graph of making. All right. Let's graph this parabola. Let's find the point and the vertex and all the components. So y is equal to x squared minus 3x plus 7. By the way, you can do all this in roll form alpha as well, but I want to do a little bit more. So let's take a look at the point 3/2 and 19/4. So if we just graph that, this is what we see right away. And let's include the focus and the vertex, or directrix, sorry. It's kind of small. But if we take a look at any point on this parabola, you can imagine how this distance would look like if we measured the distance from the point to that point on the parabola and the distance from that to the directrix. Okay, it should be the same distance. Okay. Can't really show that without computing it, but we'll just leave it at that. So they would have the same distance from the focus to any point on the parabola and that point on the parabola to the directrix. So we can have these things go sideways too, and if it does, then it just means that the y is going to be squared instead of the x. and then x is not going to be squared. So those are the things to start watching out for when you're looking at these conic sections. Is you want to be able to look at a conic section equation and determine, is this going to be a parabola or is it going to be something else? And that's going to depend on just looking at the variables x and y. So let's see if we have a quick example of a sideways parabola. Oh, here it goes. I call it a theorem for some reason. So parabola with vertex b comma c, focus point is c plus 1 over 4a comma b, and directrix is given as an x equals something, so that's a vertical line. X is equal to c minus 4a, and then your equation is going to be an x that's by itself, and then the y that's going to be squared. So this is, you probably want to write this as a function of x. This is going to be sideways parabola. So directrix, focus, and your parabola would be going sideways. All right, same sort of equation, same sort of rules. We can recreate the same thing we did, except change the x and the y's. You just have to complete the square on the x side, or on the y side in this case, and then just work it out that way. All right. So it's going to be important to look at the variables x and y and to see which ones are squared and which ones are not squared. And so the ones, if both of them are squared, then you're looking at one of the other forms, either an ellipse, a circle, or a hyperbola. And then the sign in front of them, whether it's positive or negative, is going to tell you whether you're looking at an ellipse or hyperbola. So all that stuff is going to be something that you want to start getting used to. Just looking at a function or looking at a relation between x and y and saying, oh, that one's an ellipse, or this one's a parabola. Okay? Without having to graph it. All right, I think that's good. We got a minute before the end of class. Any questions? So next time we're going to dive on ellipses, circles, and then hyperbolas, and then we're going to do some calculus on these things. You have homework due on Sunday, and you have labs due on Monday, or Tuesday. So make sure you do them. Good luck.